Hi there, Ulysses folks. My name is Haoling. I'm glad to have the opportunity to introduce our experiences of landing machine learning onto market-scale mobile malware detection. I'd like to show you our discoveries, choices, and use techniques along the way of building and deploying a malware detection system that has been checking 10,000 apps per day at a real app market since March 2018. Now, let's get started. Everyone is familiar with app markets. They are crucial to today's mobile ecosystem. We use them to download and update apps almost on a daily basis. In turn, they have also become a convenient channel to spread malware. Worse still, since we tend to put great faith in these app markets, especially well-known ones like Google Play, they in fact lend credibility to malware published on them. To address such a dilemma, companies and researchers have devised various automated techniques over the years. In the past decade, machine learning solutions have drawn a great deal of attention, as they are considered to be more automated and robust compared to traditional techniques. There are many kinds of machine learning techniques that have been studied, from fingerprint-based antivirus checking, static code inspection, to dynamic behavior analysis. Although ML techniques seem so promising and effective, we in fact haven't seen a single report of their deployment and effect at a real app market. Not knowing the real-world challenges impedes further advances. In particular, challenges of incorporating an ML solution can be manifold, such as feature selection, analysis speed, developer engagement, and more, making the situation even more complex for app markets. To bridge this gap, we intend to share our experiences on building and deploying an ML-powered solution in a real app market. In this work, we collaborate with a major Android app market called the Tencent market, who enables us to access large-scale dataset of apps. In total, the dataset contains the malicious labels of 500,000 apps submitted to Tencent market and reviewed by its own sophisticated app review process. To build a desirable ML-based detection system at market scales, we focus on a lightweight and scalable feature extraction design, API-centric dynamic analysis, which monitors Android API invocations at an app's runtime. To do so, we construct a dynamic analysis engine based on Google's Android emulator. We use the Monkey UI exerciser to generate UI events for apps, and the Xpose hooking framework to track apps' API usage during their runtime. With the dynamic analysis engine, we acquire the API invocations of a given app and convert it to a one-hot feature vector for model training. However, naturally, tracking all 50,000 APIs in the Android SDK incurs too high an overhead. So, the problem is, which APIs should we track? To understand that, I'll next take you to our API selection strategy. First, we attempt to rank all the 50,000 APIs by their correlations with the malicious of app. To measure correlation, we use the Spearman's rank correlation coefficient, or SRC for short. As we can see in the figure, only 260 APIs exhibit non-trivial correlation. We next experiment to see what impact can the number of tracked APIs bring to the time course. We rank all APIs according to their SRC and measure the time course when doing data collection. We notice a trimodal distribution in their statistical relation. The time course experiences three different stages of growth, possibly because the gradual enrollment of malicious correlated APIs, frequently used APIs, and hardly used APIs. We then look into the impact of API selection on ML model. We implement 9 mainstream ML models and feed our data collected by tracking all 50,000 APIs into them. As shown in the table, we notice that random forests can best balance precision, recall, and training time. Considering its good generalization ability, we then choose random forest as our classifier. Further, we attempt different numbers of APIs for model training and reveal something intriguing. We notice that as the number of APIs reaches the threshold of 490, the precision and recall both begin to drop, possibly due to the impact of overfitting. This suggests that strategically tracking fewer APIs can not only benefit the detection speed, but can also improve the detection accuracy. Based on the previous discoveries, we formulate our key API selection strategy as follows. First, we pick those with the highest correlation with malware. Next, as APIs protected by critical permissions are often relevant to sensitive user data, we pay special attention to them and select our APIs related to restrictive permissions. Then, we focus on APIs that perform sensitive operations like executing shell commands. Finally, we combine the three sets and obtain our key APIs. As shown in the right, the three sets have little overlap, together leading to a total of 426 key APIs. Using the selected key APIs, we collect apps runtime data and feed them to a random forest model to see the outcome. The result is rather promising. We achieve an average analysis time of 4.3 minutes. Also, we can obtain a precision of 96.8% and a recall of 93.7%. However, we realize that simply tracking framework APIs has inherent limitations. Attackers can bypass API invocations through other mechanisms. In practice, we notice two such alternatives. First, hidden and internal APIs triggered by special techniques like Java reflection. Second, IPC through intents that leverage other apps or services to perform sensitive actions. To uncover them, we add two auxiliary features to our existing feature vector, permissions and use intents, since permissions are necessary for invoking internal APIs. As a result, experiment shows that the combination of key APIs, permission, and use intents can further boost the precision and recall in practice. Based on our results of feature and model selection, we implement our malware detection system called the API Checker. First, we attempt to optimize the emulation infrastructure using the analysis engine to enhance runtime performance, as we noticed that 30% of apps require more than 5 minutes to analyze. We attribute that to the full system emulation of default Android emulator built on top of Cameo. To address this, we architect a solution that combines the power of Android x86 and the dynamic binary translation. In detail, we run Android x86 on powerful servers and use dynamic binary translation to translate apps' original ARM instructions to x86 instructions. In this way, we can run apps directly on Android x86 with high efficiency. In our deployment, we run our lightweight emulators on a single 20-core server and pin each emulators to a core. In very rare cases, dynamic binary translations may face incompatibility problems, leading to app crash. When that happens, we roll back our emulator to Google's default Android emulator. Consequently, we are able to analyze an app in around 1.3 minutes, saving around 70% of the detection time. We apply the optimized emulator to API Checker and evaluate its performance in Tencent market. API Checker has been running since March 2018. It can check around 10,000 apps per day using a single commodity server. Evaluation shows that our precision and recall is over 98% and 96% respectively, with little fluctuation. Also, we know that it's necessary to update our selected key APIs. Currently, we update the key API set every month using the original dataset and newly submitted apps. As shown, we can observe slight fluctuation in the number of key APIs during its running. When it comes to machine learning solutions, an inevitable problem is false result, or specifically false positives and false negatives. We too face them in practice. We choose to actively and fully avoid false positives by manually checking them every day, as they greatly impact developer experiences. Fortunately, most of them can be quickly vetted based on their previous versions. In fact, we need only to inspect less than 80 apps each day. On the other hand, false negatives can pose threats to end users and can hardly be avoided. For them, we observe that most have fairly simple functionalities, such as displaying advertisements or accessing certain websites, which are commonly considered to be mild threats to users. As they have little effect on the regular operations of Tencent market, we choose to only passively mitigate them based on user reports. To obtain deeper understanding of selected key APIs, we rank all key APIs using the Gini importance indexes provided by the random forest model. We list the top 20 APIs in the figure and find that they mostly fall into the following three categories. I summarize our experiences of building, deploying, and maintaining API Checker at a real app market in 5 aspects: feature selection, feature engineering, app analysis speed, developer engagement, and ML model evolution over time. We believe they are the key challenges to building a similar large-scale ML system. What's more, we know that failure in any of the aspects would lead to the failure of all attempts, namely wooden barrel effect. To conclude this talk, I list our work's major contributions here. Also, we have released our dataset, ML model, and tool to the community. You are most welcome to check it out. Thank you.